Variable frequency drive, or VFD, tripping on bus overvoltage can stem from several potential causes. Firstly, consider a loose or corroded neutral connection. This can effectively create an open neutral, which leads to voltage imbalances across the phases. Secondly, a faulty neutral conductor could be to blame. If the neutral conductor is damaged or undersized, it won't be able to properly carry current, again contributing to an open neutral situation. Thirdly, an unbalanced load is a common culprit. When one or two phases are significantly more loaded than the others, it causes voltage fluctuations that can trigger the overvoltage protection. Fourthly, a capacitor bank malfunction can inject voltage distortions and imbalances into the system, mimicking the effects of an open neutral. Fifthly, harmonics generated by the VFD itself or other equipment connected to the same electrical system can interfere with neutral currents and cause voltage imbalances. These harmonics can distort the voltage waveform and lead to nuisance tripping. To systematically address this issue, follow these steps. 1. Verify the neutral connection. Carefully inspect the neutral connection at the transformer, the motor control center or NCC, and the VFD itself. Make sure all connections are tight and free of any corrosion. Corrosion can significantly increase resistance and impede current flow. 2. Check the neutral conductor. Examine the neutral conductor for any signs of damage such as cuts, abrasions, or melting. Also, verify that the conductor is properly sized for the expected load. An undersized conductor can overheat and fail, leading to an open neutral. 3. Balance the load. Analyze the current draw on each of the three phases. If there is a significant imbalance, try to redistribute the load more evenly. This might involve moving circuits or equipment from heavily loaded phases to lightly loaded phases. 4. Inspect the capacitor bank. If a capacitor bank is present, test each capacitor individually to ensure it's functioning correctly. Failed capacitors can introduce voltage distortions and imbalances. 5. Minimize harmonics. Implement harmonic filters or other mitigation strategies to reduce harmonic distortion. Harmonic filters are designed to block specific harmonic frequencies, preventing them from propagating through the electrical system. 6. Upgrade the VFD. Consider upgrading to a VFD with a lower harmonic profile or built-in active front-end, or a FE. An AFE VFD actively shapes the input current waveform to minimize harmonic distortion. 7. Contact the utility. If all other steps fail to resolve the issue, contact the utility and provide them with detailed documentation of the problem. They may be able to diagnose and resolve the issue on their end, particularly if it stems from a problem with the distribution system. Also, ensure proper ground fault protection is in place to detect and isolate any potential ground faults. Ground faults can contribute to voltage imbalances and other power quality problems. Perform regular maintenance checks on all electrical components, including the VFD, MCC, and transformer, to prevent potential problems. Regular maintenance can help identify and address potential issues before they lead to equipment failure or nuisance tripping. Conduct load testing to verify that the system can handle the current loads without causing voltage imbalances or other issues. Load testing involves simulating the actual operating conditions of the equipment and measuring key electrical parameters to ensure they are within acceptable limits. Let's delve deeper into each of these possible causes and solutions. Firstly, a loose or corroded neutral connection presents a high resistance path for current. The neutral conductor is intended to carry the unbalanced current back to the source. When the connection is compromised, the voltage and the phases become skewed. The phase with the lightest load sees an elevated voltage, while the phase with the heaviest load experiences a voltage drop. Visual inspection is critical, looking for discoloration, pitting, or loose hardware. Thermal imaging can also be used to identify hot spots, indicating a poor connection. Repair involves cleaning the connection surfaces, tightening the hardware to the specified torque, and applying an antioxidant compound to prevent future corrosion. Secondly, a faulty neutral conductor can be undersized for the anticipated imbalanced load, or it may have sustained damage such as cuts, nicks, or corrosion along its length. The National Electrical Code, or NEC, provides guidance on conductor sizing based on the expected load and the type of insulation. If the conductor is too small, it will overheat, leading to insulation breakdown and eventually conductor failure. Damage to the conductor reduces its effective cross-sectional area, increasing its resistance and causing voltage drop. Replace the faulty conductor with one of the correct size and type, ensuring that all connections are properly made and torqued. Thirdly, an unbalanced load is a common occurrence in three-phase systems. Ideally, the load should be distributed equally across all three phases. However, in practice, this is rarely the case. Single-phase loads such as lighting, receptacles, and small motors are often connected unevenly, resulting in an unbalanced current flow. This unbalanced current flows through the neutral conductor, creating a voltage drop that affects the voltage on each phase. Measure the current on each phase using a clamp on ammeter. Calculate the percentage of imbalance using the following formula. Imbalance equals the maximum deviation from the average current divided by the average current, all multiplied by 100. If the imbalance exceeds 10%, redistribute the load to balance the current flow. This may involve moving circuits or equipment from heavily loaded phases to lightly loaded phases. Fourthly, capacitor bank malfunctions can introduce voltage distortions and imbalances. Capacitor banks are used to improve the power factor of the electrical system. However, if one or more capacitors fail, the capacitance on each phase becomes unbalanced, leading to voltage distortions. Individual capacitors can fail due to age, overvoltage, or overcurrent. Check the capacitance of each capacitor using a capacitance meter. Replace any capacitors that are out of tolerance. Also, ensure that the capacitor bank is properly protected with fuses or circuit breakers. Fifthly, harmonic distortion is a significant concern in modern electrical systems, particularly those with variable frequency drives, or VFDs. VFD use electronic switches to control the voltage and frequency of the power supplied to the motor. These switches create harmonics, which are frequencies that are multiples of the fundamental frequency 60 Hz in the United States. Harmonics can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with electronic devices. Measure the harmonic distortion using a power quality analyzer. This device will display the total harmonic distortion, or THD, as well as the individual harmonic components. Implement harmonic filters to reduce the harmonic distortion. Harmonic filters are designed to block specific harmonic frequencies, preventing them from propagating through the electrical system. There are two main types of harmonic filters: passive filters and active filters. Passive filters use inductors and capacitors to create a resonant circuit that blocks the harmonic frequency. Active filters use electronic components to inject current into the system that cancels out the harmonic current. Consider upgrading to a VFD with a lower harmonic profile or a built-in active front end, or FE. EFE VFD use advanced control techniques to minimize harmonic distortion. Sixthly, consider upgrading the VFD. Replacing an older VFD with a newer model that incorporates active front end, or FE technology, can drastically reduce harmonic distortion. AFE VFD actively shape the input current waveform, resulting in near unity power factor and significantly reduced harmonic emissions. This not only improves power quality, but also reduces stress on other electrical equipment connected to the same system. AFE technology actively controls the input current waveform to match the sinusoidal voltage waveform, minimizing harmonic distortion and improving power factor. This results in a cleaner power supply and reduced stress on the electrical grid. Contacting the utility company is crucial when all other diagnostic and corrective measures have been exhausted. Provide the utility with detailed documentation of the issue, including voltage recordings, harmonic analysis reports, and a description of the steps taken to resolve the problem. The utility may need to investigate a distribution system to identify and correct any problems that are contributing to the overvoltage condition. This could involve checking the transformer connections, inspecting the distribution lines for damage, or adjusting the voltage regulator settings. Proper grounding and bonding are essential for electrical safety and power quality. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection devices to operate and clear the fault. Bonding connects all metal parts of the electrical system together, creating a low impedance path for fault current. Verify that the grounding and bonding system is properly installed and maintained. Check the ground electrode resistance using a ground resistance meter. The ground electrode resistance should be less than 25 ohms. Inspect all grounding and bonding connections to ensure they are tight and free of corrosion. Regular maintenance is critical for preventing electrical problems. This includes visual inspections, thermal imaging, and electrical testing. Visual inspections can identify loose connections, damaged wiring, and other potential problems. Thermal imaging can detect hot spots that indicate overheating or insulation breakdown. Electrical testing can verify the performance of the electrical system and identify any deviations from normal operating conditions. A load study is an analysis of the electrical loads in a facility. This information is used to determine the size of the electrical service, the size of the conductors, and the size of the overcurrent protection devices. A load study can also identify areas where the electrical system is overloaded or underutilized. Perform a load study to verify that the electrical system is properly sized for the expected loads. Measure the current on each phase using a clamp on ammeter. Record the maximum current demand over a period of time. Compare the measured current demand to the capacity of the electrical service. If the current demand exceeds the capacity of the electrical service, consider upgrading the electrical service. Also, ground fault protection is designed to detect and interrupt ground faults. A ground fault occurs when current flows from a live conductor to ground. Ground faults can be caused by damaged insulation, loose connections, or water intrusion. Verify that the ground fault protection system is properly installed and tested. Test the ground fault protection system using a ground fault tester. The ground fault protection system should trip within the specified time and current limits. By following these steps, one can effectively troubleshoot and resolve variable frequency drive tripping issues caused by bus overvoltage, ensuring reliable and efficient operation of the electrical system.